Now, we want to look at ways to quantify energy and power in waves. And I'll start with a puzzle. This light bulb gives off a couple of watts of visible light. This laser pointer gives off about 5 milliwatts of visible light. So this bulb gives off roughly 1,000 times as much energy as the laser pointer. But if I shine the laser pointer on this tile, the spot from the laser pointer is significantly brighter than the light from the bulb. The difference is a question of intensity. The power from the laser is not that great, but it's concentrated in a tiny area. And so in talking about waves, we want to consider not just power, but intensity, which is the ratio of the power to the area. Now, this laser pointer focuses the light in the same area, but it's about 20 times as much power. So this laser pointer makes a very bright spot indeed. And as a matter of fact, the intensity, the power divided by the area, is so large, if I shine it on this balloon, it's enough to pop it. Oh yeah! So that's a question of intensity. Not that much power. It's only 100 milliwatts, but it's focused in a tiny spot. And so the ratio of the power to the area is quite large. Now, I have these little solar grasshoppers here. And the light from this bulb is shining on the grasshoppers, but they're not dancing. So what could I change about the light bulb in order to produce enough intensity on the solar cells to cause the grasshoppers to dance? We'll give you some choices. And this is something we haven't talked about formally, but you have a qualitative understanding of. As the light comes out of this bulb, it starts at a point and it spreads out. And as it spreads out, the power stays the same, but the area over which it spreads gets bigger, and so the intensity goes down. And we'll see an expression in the book for calculating the power from a spherical wave. And as it spreads out, the area gets bigger, and so the intensity goes down. So one way to make the intensity bigger, enough to run the grasshoppers, is just to bring it closer. And when it's close enough, it's time for some dancing. But there are more options available to you. The light that comes out of this light bulb spreads out, but I can take some of it and I can capture it with a lens. And this lens focuses the light, brings it back together. And when it brings it back together, I can make it intense enough at a spot to make a grasshopper dance. And so what the lens is doing is capturing a certain amount of light, bringing it to a smaller area, and so therefore increasing the intensity. And that's another option. I can use a lens to gather up more power, focus it into a smaller area, and then I can have enough intensity to make the magic happen. Now, when we talk about sound waves, we have a totally different way of dealing with intensities. Instead of talking about the intensity of sound waves, we usually talk about the sound intensity level, and here's why. So I'll turn this on at the smallest intensity that I can sense. Okay, so I'm able to sense that pretty handily. But now if I was to take this signal generator and crank it up so that the intensity was at a level that I found it uncomfortable, and I'm not going to do that. But if I did, if I turned this up and made it louder, and I made it loud enough that I found it uncomfortable, if I did that, I would increase the intensity not by a factor of 1,000, not by a factor of 1,000,000, but by a factor of 1,000,000,000. And because the intensity changes are so large over the range in which your hearing is sensitive, we use a different scale. We use the so-called decibel scale, which measures sound intensity level, and it uses logarithms. And that's something we'll show you how to compute in the book. So when you've heard about sounds as being measured in decibels, it's this logarithmic scale. It goes from 0 decibels up to 120 and higher. But it's a logarithmic scale, so that actually corresponds to a significantly larger range of intensities. A quick preview of what we'll talk about next time. We have a spring here that's heading towards the camera. If I shake a wave, it goes down, it bounces, and it comes back. So if I continue to shake waves going in this direction, they overlap with waves that come back towards me, and as they do that, I can produce this very special kind of wave called a standing wave. And that's something which we'll talk about in the next segment.